What's up, everybody? Welcome to part 3 of this tutorial series on using the KITTI Odometry dataset with Python and OpenCV. In the first video, I covered the fundamentals of camera projection matrices and how they take points in 3D space and project them onto a flat 2D image plane for a camera. And then in the second video, we talked about how we can handle the dataset easily with a convenient class object that we made in Python that'll put all the data that we need right at our fingertips so that we can move on now and go into doing visual odometry with that data. And so we're going to do that by, first we're going to look at this picture just to review how we're taking a point XYZ in 3D space and then we're projecting it onto this 2D flat image plane of the camera. And so once we've done this, we have lost all of our depth information because we projected it onto a flat plane by dividing the depth out of the x, y, and z coordinates, which gave us our coordinates on this flat plane where all of the depths are the same. And so the way that we do visual odometry in this case, what we're going to be doing is we're going to estimate the change in pose of the camera between the last frame and the current frame by taking the image from this, the previous frame and then reprojecting the features that we're tracking in that image back into 3D space. And then we're going to solve for the rotation and translation, so the change in pose of the camera into the next frame that best satisfies where those features are now found in the new image plane. So in the next frame, where those features are on the image plane based on where we said they were in 3D space in the coordinate system of the last camera's frame, in the last frame. And so over time, we accumulate these pose changes, these one frame pose changes, and then if we put all of them in reference to the first coordinate frame of the camera's first position, then we have tracked the motion of the vehicle in the global coordinate frame, which is the coordinate frame where the camera is when it starts over time. And so in each subsequent frame, we'll need to perform this operation where we pick features that are distinct in the image, and then we're going to reproject them into 3D space, and then using their locations in the next image frame, we will figure out the best solution for how the camera has moved between the two frames. And so in order to do this, we're going to need a depth estimate because, like I said, when we projected down onto this 2D plane, we lost our depth information. And so we need to recover that somehow. And there's various ways to go about that. But the classic approach is using a stereo camera head, where you have two cameras that are a known baseline apart, and then you use the difference in locations of the same points in those two pictures in order to measure what they call disparity, which is the difference in horizontal location between where the same thing appears in two images. So like if your finger's right in front of your face and you shut one eye and you shut the other, your finger's going to move more. And if it's really far away and you shut one eye and shut the other, it moves less. So based on how much disparity a point in your image has between your stereo pair of images, you can then estimate depth. And because the more disparity you have, the closer it is to you, the less disparity you have, the further it is away. And so here's how we're going to do that. To give a visual representation, I've made this helpful graphic down here that shows how this works. And so we've got two cameras, the left camera and the right camera, and they're both looking at this point O in 3D space. And so this point O is getting projected onto the left camera's image plane here at XL and projected onto the right camera's image plane at XR. And this is the baseline between the two cameras, which we know. And this is the focal length of each of these cameras, which we know from the camera intrinsic matrix that we have been given, or in some cases that we've calibrated our cameras to find. In this case, we were given it by the data set. So what we can do is, knowing our baseline, we can use similar triangles rule to reconstruct Z, which is the depth. That's exactly what we divided everything by when we projected everything down onto a flat image plane. So that's what we need to multiply back onto our image features to reconstruct their actual 3D locations in metric space. And so using similar triangles, what we can do is that with similar triangles, the proportion of sides, the ratio between two sides, stays the same as you scale a triangle. So this little blue triangle here between the left camera and its image plane, and then the large blue triangle that goes out to the actual metric Z and X coordinates of point O, have the same ratio between their sides. And so we can write that Z divided by F, so the longer adjacent side divided by the adjacent side of the smaller triangle, is the same as X divided by XL. And so we write that here. So Z over F is equal to X over XL. And then we can write the same thing for the orange triangle for the second camera and say that X minus B, which is the length of this side, which is left over when you subtract the baseline away from X. And so again, Z, this is the same Z length here. Z over the focal length again is going to be equal to X minus B over XR. And so we've got that here. And so when we rearrange things a bit, well, first, so we can define disparity as being the difference when you subtract XR from XL. And so we just, write that here. D is disparity. It's equal to XL minus XR. And so if XR happens to be negative, then you're subtracting a negative number, so you're actually adding them together. And you can see that will result in a larger disparity. And that would just mean that the point was located over here. So this math works out either way. And so rearranging the two equations that we wrote, given our similar triangles, we can cross multiply Z times XL equals F times X here, and then the same Z over F cross multiply, we get ZXR equals F times X minus F times B, because we just distributed F into this statement here. And so we, what we can, oops, I kind of got away from me there. Hold on a second. We can substitute in ZXL for FX, F times X here. So we write that in, ZXR equals ZXL minus FB, and this is the focal length times baseline. And then we'll just move FB over to this side, subtract ZXR over here, and then we'll factor out the Z and say FB equals Z times XL minus XR. And so earlier we said that the disparity is XL minus XR. So we'll just plug that in here, and we get focal length times baseline equals Z times disparity. And then we can solve for Z, which is what we want, and get Z equals focal length times baseline divided by disparity. So if our focal length and disparity are measured in pixels, then the pixel units will cancel, and baseline is measured in meters. Then we'll be left with a measurement in meters of Z, which is what we want, because then we can use that to multiply back in to our X and Y coordinates on the image plane and reconstruct our 3D space of our feature points. And so that will give us the 3D locations of points in the camera's current frame, or the previous frame that we're looking at, that we can then use to look at the next image frame and find where those points are located in the new image plane, and then solve for the change in rotation and translation that will best satisfy where they're now currently found. So to find disparity, there's just a convenient way to do this with OpenCV. So you don't have to do this all by hand. OpenCV has a function that allows us to do this. And so that's where we're going to start with this tutorial. We've got over here just a pretty fresh notebook. We've got importing CV2, datetime, matplotlib, numpy, OS, and pandas, so that we could load up our dataset handling class here. And so this is the dataset handling class that we made in the last video. And so this is all we need to start. I think they're already loaded, but I'll just load them again. All right, so we're off. So what we need to do is we need to, there's two different stereo matchers, or what they're called in OpenCV, that basically scan through your stereo set of images and figure out where the same pixels are located in both image, and then it measures the horizontal disparity between those points. And so if you want to know more about what's happening under the hood, then you should go to the OpenCV documentation and kind of read through that. They've also cited the literature of the research that they use to construct these functions. So that's going to be outside of the scope of what I can cover here. But if you're really curious, it's available there, and I'll have links in the description of the video to bring you where you need to go if you want to find that. But what we'll do is we'll just exploit the fact that OpenCV has provided us with these tools that are already optimized, they work, and so we can just go ahead and start using them. So I'm going to add a little bit of space here so that we're not always looking at the bottom of the screen. And so what we're going to wrap these functions up into our own function called compute left disparity map. And we're going to take an image left. Ooh, I'm actually going to abbreviate that. Image left, image right. I'm going to say matcher equals BM. Well, maybe I'll just, yeah, okay, I'll explain this as I go, but I'm going to start with all of our arguments here so we don't forget anything. I always like to include a verbose flag in my functions, because if there's things that, sometimes I want to diagnose what's happening or how long something's taking in my function, then I can set that to true. I'd rather usually have it on false though. And so that way, once we start using this in a giant loop, because there's, 4,500 frames in our first sequence that we'll be using, so we don't want it to be reporting its whatever's happening inside of this function 4,000 times. So, okay, and then RGB is false because we're going to be using grayscale pictures, and I went into all of the reasons why, namely because the disparity matching and feature matching that we'll be using, the functionality in OpenCV, expect grayscale pictures. And that I'm putting an RGB flag in here just in case you want to take this function later and apply it to other images or databases that may be in color, but you still want to compute a disparity map, then you'll be able to do that. But in this case, it won't even matter to us. So we'll just go ahead. So maybe I can go ahead and just load up OpenCV Python, because I want to point out, because I'm going to start writing some numbers up in here, and I don't want you to be like, you know, where are you getting these numbers from? I'll show you. I got them straight from the documentation for OpenCV. So you can see here they've got, you know, the class here, and then all of the things that you pass into it. And then they have recommended values, except they're all set to 0 here. So I'm trying to think. They have a tutorial on this, which is actually where I got the values from. So anyways, you know, to save a little time here, just take my word for it that the values that I'm going to use work well, and that I found them in a tutorial for using these functions. And so we're going to say sad window, let's add a little white space here, equals 6. Number of disparities equals the sad window times 16. And block size equals 11, and matcher name equals matcher, because I'm actually going to reuse that variable name. So sorry if that's a little confusing, but it's much better to put it this way. Okay, so again, like I said, these values, I've picked them because they work well. Feel free to, you know, do some personal research, tweak these values, see if they can improve the performance of what we'll be doing here. And if they do, I mean, let me know. Drop a link or drop a comment, and, you know, tell me if you found some values that work better for the task here. But we're going to run with these. So so I put in this matcher argument because, like I said, there's two different classes that I'm aware of in OpenCV to calculate disparity maps, and that's stereo SGBM and there's stereo BM. And we'll see the difference in just a moment. So we'll set up an if matcher name is equal to BM, then we'll set up our matcher object as being cv2.stereobm create num disparities equals num disparities, and then we will also say block size equals block size. Now, unfortunately, OpenCV Python, as you can see when I open this up, has very, well, this is not so bad. It's their documentation, doc strings are kind of a little hard to look at. So you can see the names of the things that you're supposed to put in here, and they have a description here. It's not always quite so explicit. But yeah, so, you know, feel free to read this, and also, you know, read the documentation. I've heard people say that, you know, the documentation for OpenCV Python is not as well written as the documentation for C++ OpenCV, because that's sort of where a lot of people are at when they're using this. So, you know, it takes a little bit of hunting around to find the ideal values for things. But like I said, we'll start with this, and then you'll have a framework to go ahead and play around with, you know, messing with values and seeing what works and what doesn't. So if our matcher name is SGBM, then instead of using the stereo BM, we'll be using the stereo SGBM. And you have to say create with the way OpenCV works. So num disparities equals num disparities, and we'll say min disparity equals 0. We'll say block size equals block size that we set up earlier. And then, okay, P1 equals 8 times 3 times the SAD window. SAD stands for the sum of absolute differences, which is how it is comparing the images. And like I said, that's a little outside of the scope of what I can explain here. But if you're curious, they have, you know, references to the literature that they've used to set these functions up. So, you know, if you really want to dig into the nitty-gritty, that's going to be where you want to go. And also, the way I found these particular values should be right over here. This must just not be the same piece of the documentation I was looking at. You see what I was talking about, that the documentation for OpenCV Python are just not exactly clearly written as it could be. Oh, here it is. Okay. So where some reasonably good P1 and P2 values are shown, like 8 times number of image channels times block size, and yeah. So in this case, actually want to check on the number of image channels we really do have, because that's interesting, because these are grayscale pictures. But okay, I didn't even load a handler class, so let's go ahead and call one and say dataset handler. And is there any special things we need to tell it? I think the sequence number and low memory is already set to true. That's what we're going to run with, because not everybody has 1,000,000 gigs of RAM in their computer. Okay, so we got a handler. We can go ahead and say plt.mshow handler dot what do we have? First image left. Take a look. Here's a picture. So I want to see what the shape of that is. Handler dot first image left dot shape. Yeah, so this is definitely just a single channel. So it's possible that you could tweak these values, but you know, I've already run with this and it worked great. So we're just gonna run with this for now. And okay, so let's finish what we're doing here. Mode equals cv2.stereo sgbm, and this is the one I was using, mode sgbm 3-way. I think that that's probably the most accurate. It may also be the slowest. So again, I won't do too much reading of the documentation here in this video, but you know, you can look into all these things. And so what we're going to say is if RGB, then we're going to convert the images. This is not really going to come in handy with our data set, but when I make functions, I like to have them work for, you know, other things later on. So this is how you convert color to grayscale in OpenCV with Python, which is something that will come up if you end up using OpenCV more outside of the context of this dataset and tutorial series. So yeah, they have these like flags that are attached to CV2. So you say CV2.convert color, then you tell it the image that you want to convert, and then you say CV2.color underscore, and then oops, you can see that they've got all of these different conversions where they, you know, green red to blue green red alpha, GR to gray. I mean, so basically any image format that you have that you then want to convert to grayscale, you can find it in here, or rather not just to grayscale, but any other image format. So generally, I think that blue, green, red is something that comes up a lot. So that's just something you have to check on your own to make sure that you know the format of the images that you're using. So you then have to modify this. accordingly, because you might be in RGB and you want to turn to grayscale, then you would have to say RGB instead of BGR. So getting caught up in the specifics here, but we're getting there. This is one of the sort of a lot happening under the hood with the stereo matchers in OpenCV. Okay, so that if we told our function that RGB is true, then we would go ahead and run a grayscale conversion. So what I'm going to do is I'm going to set up a start timer and say datetime dot now. This is how I time things. I know there's other ways, but that's just how I learned. Okay, so then we get the disparity left equals matcher dot compute image left, and then you pass image right. Okay, so this is a bit tricky here, and it's very, very important. So you're gonna want to cast it as type np.float32, and then you want to divide by 16. And this is because I believe that they're doing the math in OpenCV behind the scenes. They've converted it to possibly like integer math or something like that to make it easier, like faster. And so in order to get it back into the values that it's supposed to be, you have to divide them by 16. And so it's important to note. So don't forget that. Otherwise your values aren't going to make sense. So, and then we're going to end the timer, datetime.datetime.now. And then we'll say if, let me do a little white space here, if verbose, then print time to compute disparity map using stereo, I'm going to say matcher name upper, because that's going to make it print out the way that it looks. And we'll say end minus start. So this way we can compare SGBM and BM, since we made the function to where we can use both. And later on we'll be able to compare the actual performance that we get using one or the other. So that'll be nice. So we have a nice wrapper function here that should be ready to go. No, it isn't. What do we got? I forgot a comma. All right, so here we have a function to get our left disparity map from a stereo pair of images. Well, let's go ahead and take a look at what we get if we run this. So we'll say disparity equals compute. Kind of made that a long function name. I got it from somewhere else, and I've just been using it ever since. So feel free to abbreviate that a bit. But I just I didn't want to go changing it, because then I guess I could have done a find and replace all, but I don't know. You get used to using a certain function name, and you don't want to go messing with your strategy. All right, so we're just going to pass all of our arguments the way we like them. In this case, we're going to start with matcher equals BM style. Sounds really appealing. And okay, so then we do plot.figure. I'm gonna say fig size equals something that we can see, and plt.imshow the disparity map. Right on. And just so you know, so you don't get weird text printout, if you put a semicolon after whatever plt dot something that you do without having to say plt.show, because you get that, I'll show you. You get that kind of annoying little return here that you don't need. And so, you know, I'm sure most people know that, but yeah, put a semicolon and it's gone. So that's pretty cool. We have a disparity map here, but it's a little disintegrated. There's a lot of missing areas where the disparity doesn't seem like it's really come through. And so for the most part, though, we can see the image. We'll go back up and look at our image, and why not go ahead and dang it. so we can see what we're looking at a little more clearly. Yeah, okay, so here's our little mopedist, motorcyclist guy, car, trees, apartments, and yeah, so here's the disparity map that we got from our stereo BM disparity function from OpenCV. So that's very handy. You know, this is what's great about OpenCV is that it's an open source computer vision package where they've got a lot of the essentials that you need to do all kinds of things with computer vision and lots of manipulations of images and that kind of stuff. It's all built in and it's open source. And so definitely something really worth knowing your way around in. And so, you know, I'll just be touching on the things that are useful for this application, but there's a lot of good tutorials out there. And also, I was kind of talking trash about their documentation because honestly, it is very confusing. But at the same time, they also have like lesson material, like articles written about how, like, walking through the theory and the practice of using their package to do various things, and those articles are actually very well written. So I will have some links in the description to those articles because they're actually very informative. The documentation itself is a little more confusing, but the articles are definitely something that I found to be very useful. So I'll be linking to those. And so look at this. This looks a lot nicer. This is using SGBM. And we can see that all those gaps have been filled in. Things are looking a lot more clear. Still not crystal clear. It's still, there's a bit of jarble happening here. But comparably, there is a night and day difference between these two. And so let's look at that timer that I set up. So the stereo BM took 0.02, so 2.5 hundredths of a second, whereas stereo SGBM took 7.3 hundredths. So this is that comes out to, you know, 2.5, or I don't know, a little under 3 times slower. So when speed is essential, which it is when you're doing real-time visual odometry, this is something you might want to take into consideration. And so, well, how will your accuracy do? So obviously stereo BM is missing some information here. But if we're finding a way to filter to make sure that whatever features we're matching in one image versus another, that we make sure that we're only using features that fall in areas where we do have good disparity estimation, then that won't be so big of a problem. But we'll find that there is a slight performance improvement using SGBM because I think the estimations themselves are better. But the fact that there's all these holes here just means that these are areas where we can't use features in the image because we can't realistically reverse compute the depth of that part of the image, and so therefore we won't be able to reproject a feature in that part of the image into 3D space. It won't be useful to us. So we have this purple rectangle here on the left side, and let me just look at something real quick. Okay, we have a purple rectangle here, which is being caused because we're using a stereo pair of images which are the same size, and so this is where the right camera doesn't have any information because there's no overlap between the two images there because of the baseline between the two cameras. So that's obviously going to be a part of the image that's just not useful to us in general throughout the entire sequence of images of all 4,000 frames. This part of the image is not going to contain, we're not going to be able to compute disparity information there, therefore not be able to compute any depth information there. So there's really no point in calculating, or rather detecting, features in this part of the image because we'll not be able to use any of them. So that would be a waste of time. So what we want to do is we're actually going to want to mask this out when we start detecting features, and I'll go into that. But for now, let's look at what that value there actually is. So, okay, -1. So if we look at what other values we get in our disparity, so let's say disparity where disparity is greater than -1.0. Okay, let's say min. Okay, so 0. So really, there's -1s where it literally has no idea, it just has no information. And then we have 0 is our next minimum value, which is good to know. And then so let's actually ask it now, what's the minimum when we're above 0? So everything's positive or 0 except for -1s, which are obviously just throwaway information. So what's the next one up? Okay, we get a 0.5625. Good to know. So now we have some idea of what our values are looking like. And these values are in pixels. So this is the amount of difference that it's computing between what it has determined through the algorithm to be the same object or point in the image in both of the camera frames. And then this is the distance in pixels horizontally between those points. And so let's see what the max is. Okay, so like 95 pixels is about as far as things have moved back and forth, and it looks like this tree over here is the closest thing to us. So that's the thing that has had the most disparity, you know, the most parallax between the two images. So very cool. And we can see this looks really good, but you know, this is supposed to be giving us our depth information, and very much so, it appears as though the lighter colors are closer to us, and as we go away, things get darker. It's looking pretty good. We should be able to get some good depth estimation from this. So let's go ahead and look at how we can do that. So in, I think, the first video, I talked about the decomposing a camera projection matrix into the intrinsic and extrinsic camera matrices. So the projection matrix is the dot product of the intrinsic matrix dot product with the extrinsic matrix, and so it just combines them together into one matrix. And so that's nice and all, you know, packaged up, but oftentimes we actually want to decompose that matrix to find our intrinsic and extrinsic matrices independently so that we can extract information from them. So the way CV2 has a useful function for this, which is awesome. So, and the way that we do this is, okay, so we have projection matrices as part of our dataset handling object that we designed before. So if we look at handler.p, we have P0 through P3. Let's look at this one. And this is our projection matrix for the left camera that we're mostly looking at of this entire time. So if we want to decompose that matrix, we can write K, R, T, and then so there's 4 pieces of information besides K, R, and T that get returned from this CV2 function. And so if we say decompose handler.po, then we'll have these things, and let's tell it to print K, print R, and print T. Okay, so then we have K is the intrinsic matrix. This is the focal length of the camera in pixels. And we can see that it's equal in the X and Y direction because we have square pixels. If our pixels were rectangular, which basically means that the image is undergoing some amount of stretching in one direction or the other as it's processed, then these would be different. But in this case, they're the same, which is great. And then these are the image center in pixels that get added to the X and Y values. So this is you know, an important thing to discuss real quick, because when it comes to an image plane, as you're looking at me, your Z-axis is coming directly at me, And then if we're talking about pixels, then the x coordinates go negative this way or positive this way, and the y coordinates go positive downward and negative upward. And so the origin's at the center. So you can have negative x or y pixel values, but pixels are usually measured from the top left corner. So these values here are added into your x and y pixel coordinates to make it so that 0 and 0 are shifted to the top left of the image plane, and then they're no longer called x and y, they're called u and v. And so that's exactly what these numbers are telling us, is where the top left part of the image plane is compared to the origin of the camera. And it also tells us where on the image plane a ray of light coming directly down the z-axis is going to land on the image plane. I went into this, I believe, in the first video, which is that you would think that that would be the center of the image plane, but oftentimes it's not. It's offset by a little bit. And what that means is that the sensor, or whatever chip is inside of the camera, is just not perfectly aligned with the lens. There's like a little bit of offset between them. So this is why we calibrate our cameras, because we need to know this stuff. And then so in this case, the CV2 function here is decomposing our projection matrix, and it's returning R and T as separate entities. And that's okay, but technically they're both part of the extrinsic matrix, which is a transformation matrix that I talked all about in the first video, which is a 3x4 matrix that contains both R, the rotation, R, the rotation matrix, and T, the translation vector. And so if we were to horizontally stack this, which is T, on here and drop the 1 to take it out of homogeneous coordinates, then we would have our extrinsic matrix. And of course, the extrinsic matrix takes points in the global coordinate system, 3D points in the global coordinate system, and moves them into the 3D coordinate system of our camera. And since this is the left camera, which is our global coordinate system for any given frame, these values are, there's an identity rotation matrix and a translation vector of 0, because it is the global coordinate system. So there is no translation, there is no rotation. The origin of this camera is our global coordinate system. And so we're going to need to do this throughout this process, and it's a little inconvenient to have to write it this way every time. And also because if we decompose, let's say P1, then we can see that our homogeneous translation vector that it has given us here is not, they haven't turned the fourth homogeneous coordinate back into 1, which we need to do. Let's round it so we can see it a little easier. Yeah, so if we're going to think about these things in terms of the metric 3D universe where things are in meters, then we need to have this be a 1. And so the way you do that is you divide T by that value. And that's how, you know, obviously that'll turn it back into a 1. So if we say T divided by T3, now we see things in meters. And so here we can see that the this is now the right camera we're talking about, and it's 0.54 meters to the right of the left camera, which is our baseline. That's, you know, going to be the way that we reconstruct depth from our disparity maps using the math I showed you earlier. And so, you know, this is another step that we need to do to make T meaningful to us. So for all of these reasons, we're going to make our own function that wraps around the CV2 decomposed projection matrix function to give us what we want easier without having to do this every time. So we're going to say define decompose projection matrix and we're going to say that KRT, and then this other stuff that I won't go into, but you can check the doc string if you really want to know, or the documentation. And then again, cv2.decompose projection matrix, and we'll pass in that argument p. And then so t equals t divided by t3, and then we're going to take it up to the fourth value, because we're only interested in t as a 3D translation vector so that we can use it as such. We don't need it in homogeneous coordinates. So we're transforming t here by dividing it by its homogeneous scale value and then dropping the 1, which is now we're back into Euclidean space. And so then we'll just say return k, r, and t. And so this will be just helpful. Okay, so there's our little helper function. And so now we can start calculating depth. So we'll say define calc depth map. We need the disparity map. We need the intrinsic matrix for the left camera, because that'll give us our focal length. We need the translation vector of the left camera and the translation vector of the right camera, because that's going to be how we figure out our baseline. And I'm also going to add an argument here called rectified, because like I said before, I want this to work if you're using other data sets. Then you can change the value there, because I went into in depth in the first video that a rectified projection matrix does not actually function in the way that a normal projection matrix does. That when you look at a projection matrix for the right camera and it's a rectified projection matrix, then what this translation vector is actually doing is it's moving points from the right camera's coordinate system into the left camera's coordinate system, which is opposite of what a camera's projection matrix usually is doing, or the extrinsic matrix for a camera will usually take points in the global coordinate system and move them into the coordinate system of the camera that you're talking about. But so that in this case, that would mean taking coordinates from the left camera's coordinate system and moving them into the right camera's coordinate system. And that's not what this is doing. It's doing the exact opposite, because, you know, in this case, we're interested in working in the left camera's coordinate system. So they've flipped it, and that's why it's called a rectified projection matrix. It's actually taking points in the right camera's coordinate system, moving them into the coordinate system of the left camera. So you need to realize the difference, which is why we're saying rectified equals true. Because if we were going to compute the baseline with a extrinsic matrix for the right camera that was a normal non-rectified extrinsic matrix, then we would subtract the right translation, the right X translation from the X position of the origin of the left camera, which is almost always going to be 0. And so that would give us the positive 0.54 meters that we're looking for. Now, in this case, the translation vector for the right camera already is 0.54 meters, because it's actually talking about where the origin of the right camera is in the frame, the coordinate frame of the left camera. So we want to do the subtraction in the opposite direction. And, you know, really we don't need to subtract it at all, because the origin of the left camera is at 0, 0, 0, because it is the global coordinate frame. But for robustness, we want to write out the math, because normally you're looking for the horizontal X difference between their origins. And so we'll just go ahead and say that if rectified, that B equals T right 0th element, because that's the X element, minus t left 0th element, which is going to be 0. And so in this case, we're going to have 0.54 minus 0. The result will be positive 0.54 meters, which is our baseline. That's what we want because we have rectified. So if it wasn't rectified, then we would simply do the opposite. We would subtract the left translation vector, or I mean rather subtract the right translation vector from the left translation vector. So that'll do it. And okay, so F is going to be K left the 0th row and the 0th column. So first row, first column, as we saw before. Forgive the rapid scrolling, but the intrinsic matrix K of a camera has the focal length X and focal length Y and pixels down the diagonal. So we're looking for the focal length in X because we're going to be working with disparity to calculate depth in the way that I covered earlier. And so we want K left 0, 0 because that's going to give us that value. And so, okay, so now we have our focal length and we have our baseline. So when we do this math, let's look at it again the way I drew it all out. So eventually we're going to be looking for F times B divided by the disparity. So in this disparity is really going to be a whole map of disparity. So we can just use NumPy to broadcast this operation over the entire matrix, and we will get a depth map, a matrix of depth values. And so that's what we want. But so there's a trick here though, because we're dividing by D, and we saw earlier that our minimum D when we're not dealing with the -1 values, actually -1 is 0. So we can't divide by 0. And so we need to make an adjustment here or else we'll have errors. And also the fact that these -1 values that it's giving us when it doesn't know, like over here in this purple rectangle here, those aren't going to be helpful because it's like dividing by -1 is going to give you like a negative depth, and that's not going to be helpful at all. So what we're going to do is we're going to correct for where disparity left, where it is equal to 0. We're going to set it equal to 0.1, which is a really small value. And I've chosen this. I've tried other values, and basically, because we saw, I just changed the code up here, but let's change it back so that we can see this. The next minimum value we have besides 0 is 0.5, and that's, since we're dividing by these, setting this to 0.1 is essentially going to make the depth estimates at these points where it had been 0 very far away. And they will be significantly further away than the furthest points that will be given by dividing by this value, which is 0.56. So there will be a noticeable gap in the histogram between where these distances that will be calculated as being very far away will be, and the maximum real distances that we'll be getting from our good disparity measurements. And what we're going to do is we're just going to draw a line right in the sand and ignore any features found on pixel coordinates which have depths that are greater than a certain line, because we'll know that those depths are actually artifacts of our process and that they're not actually good depth estimations at all. And so we will leave them out. And so we will avoid misleading our mathematical process by doing so. And also, we want to get rid of where it's equal to -1, because like I said, that's also going to cause us challenges in our math. So we'll just set it to the same thing so that we can also filter those out in precisely the same way. and this will work nicely. So then we're going to need an empty matrix here. You could use np.zeros or you could use np.ones, and I'll just go for ones here because why not? So we'll take the shape of the disparity map, which is the shape of the image, and we will create a matrix of ones that we're going to promptly fill in with f times b divided by the disparity map. And so like I said, f and b are constants. It's our focal length in pixels times our baseline in meters divided by a matrix. And so we're broadcasting this entire operation across every value in that matrix, and we're dividing by the disparity, which is measured in pixels. And so the pixels will cancel out, and we'll be left with a map of depths that are measured in meters, which is exactly what we want. So great. And we won't be dividing by 0 or -1, and we will be able to find what this does in just a moment. So we've got that, return the depth map. Great. So let's give it a test run here. We'll say k left, r left, and t left equals decompose projection matrix handler.po, which is the projection matrix for the left camera. K right, r right, and t right equals decompose projection matrix handler.p1, which is the rectified projection matrix for the right camera, and I set rectified as standard is equal to true, so it knows already that that's the case, but would need to be adjusted if you were doing this a different way. And then so we can go ahead and load those in to our variables, and so we'll go ahead and get a depth map running and say calc depth map disparity k left, t left, and t right, just the way that we set it up here. Oh, right, this is actually where rectified, yeah, so anyways. And then we will go ahead and take a look at this. I'm getting bad with the typing here. Show depth. Okay, and so here we have our gorgeous depth map, and you might think to yourself, that doesn't look as good as the this did, and it certainly doesn't. This is much smoother. We can like see the depth happening. Everything is nicely, you know, shaded. So why is it that our depth map suddenly looks so ambiguous? And the reason is because let's look at what the value up here in the left top corner is this time. Okay, so this is yeah, you know, around under 4,000 meters away, and this is obviously where it has no idea of what anything is. And so let's see if that's also the max we would expect it to be. It is. So this is what I was talking about. If we had set this, let's say, to 0.01, then all we would have done was just be making these yellow places where it has no idea really what the disparity was, and therefore we don't know what the depth really is. We've just created this filler value of 3861 meters. And so we'll know later on that anywhere where the depth map is at this value is not good information. And so this is why we didn't need to set this any lower, because we certainly could have. We could have said 0.0001, you know, but then all that's going to do is just raise the magnitude of this number. And it's not necessary, because if we say plt.hist of, and I'm using a skin here, so I'm just going to go ahead and import import the thing that's going to make my graphs look good. If you haven't heard of Jupyter themes, you should get into it. It's much better to look at than your standard, you know, Jupyter Notebook. I like to have a little bit of ambiance with my stuff. So anyway, so plt.hist, let's look at depth here. That is definitely taking a second, isn't it? I was not expecting this to take quite so long. But we'll just let it do its thing because it's still running here, so I don't know. Okay, interesting. So, expecting, oh, you know what it is? We need to flatten this out, and that's why it took so long, because it's a 2D matrix, and we're only really interested in our flattened out values. Yeah, okay, here we go. This looks a lot more sensible. So we can see that basically between 500 meters and 3,000 meters, there's just nothing in here, and that's because these are the values that we created by adding our 0.1. We don't know what the disparity is here. Conveniently isolated all that stuff over here to the right, where we can easily draw a line later and filter out and say anything over 3,000 meters in depth, I don't want to use it because it's not good information. We're only going to pay attention to the information that we have here, which is better. So let me replot that without all the printout here. So, and an interesting thing to look into might be what is when we say depth, where depth is less than depth dot max. And it's also, and then say flatten and say max. Yeah, okay, so the maximum depth measurement that we have when it isn't saying that it's 3,861 meters away is only 686 meters away. So, we have a sizable gap that we can just razor blade right through that gap and say that we don't need anything over 3,000 because that's just bad info. So, all right, we have our depth is working. And so another important thing to mention right here is that let's go back and make our disparity map with stereo BM, and we'll get, it's got all the holes in it, with a lot more missing information. So then let's use that to make a depth map this time. Okay, so this is a lot messier, but that's okay, because if we look at the histogram of our depth, we have a lot more missing values, but they're all still over 3,000. And in this case, we have a bit of a different estimate for our max depth, but it's still in the same ballpark. So obviously there's a difference between the two approaches, but since we will be filtering out all of these missing info areas, that maybe the speed that stereo BM gives us by having a few more holes in there won't be will be okay, because we'll just be subtracting all of these areas where there's holes in the depth. And another thing I wanted to show you, just because I think it's interesting, and I'm getting this grid now because I switched themes, but whatever, we can still see, is that, so let's make our depth again, look at it. I'm just going to say plt.grid false, so it looks nice again. Okay, so remember how I said, hey, why doesn't it look good like it does up here? And I'm sure some of you already see exactly where this is going. It's just that because matplotlib is automatically scaling things between 0 and 1 basically. It's just dividing everything by the max. Let's say do this with depth, where depth is less than depth dot max, and show that. And that doesn't work. Why not? Invalid shape for image data. Well, let's just say going out of my way here to make this point. Shape is depth dot shape, and then we will just reshape this with depth shape. All right, we're gonna have a little bit of a problem here. Oh, okay, I see what's happening. We can't just filter it as conveniently like that. We're gonna have to reassign the values so that there's not just like empty spaces in our matrix. So we'll say depth, where depth equals, we have to do double equals depth dot max. And then we will set that equal to 700, because that's right in the ballpark of what we had before. And then we'll just get rid of all of this and fire that up. All right, and so still doesn't look terrific, but we can see that the higher values are further away. And this is probably because perhaps that 700 value that it came up with is also sort of an erroneous estimate. And this is the thing about stereo disparity estimation, depth estimation, is that the less disparity that gets measured, especially because we're working in pixels, the less accurate the depth estimation is going to be. So the more disparity that it measures, the more accurate it's going to be able to estimate the depth. And so, yeah, as things get further away, your estimates start getting further and further off. So, yeah, let's just for funsies, let's set this to 650 and see that. No, anyways, it looked a little nicer, you know. It was worth it. Okay, so we can see now everything is working out. We have functioning depth maps. We can filter them to get rid of our erroneous information. And now we want to go back to what I was talking about masking, because what we're going to be doing, as I've mentioned a few times, but we're really going to get into it in a second, is we're going to be detecting and matching features between our images. So detecting them by finding features which are unique and which the algorithms will be using decide will be easy to identify as being the same feature in a different image. And then we will be matching those features between the two images. And so this part of the image just has no useful information for us to do that. And so if we're telling our algorithm to search in the entire image on every frame, it's going to be searching, you know, whatever, however many thousands of pixels this is every time, and it doesn't need to do that. So if we want to save time, we want to figure out how big this rectangle is and mask our process so that it ignores that rectangle and doesn't search there. So the way we can do this is, I'm going to do it up here to make it a little easier to look at, is we can say for I pixel enumerate the depth map first row, and we'll say if pixel is less than depth.max, meaning not a yellow, bright yellow pixel, then we will say print first non-max value at index and print the index. And then we'll break the loop. So we find that our first non-max value is at index 96, which lines up with what we see visually. We've done this correctly. And so now we know that anything between the 0th and 96th column is useless to us in our depth map or in our image in general. So now we can use CV2 to make a mask. And so we're going to make a empty array and call it mask. And we're going to use mp.zeros. And we're going to use the shape of our image. I'm trying to think of... I don't think I really need to do that, but let me check real quick to see if the depth is the same shape as the image. And I'm getting down the bottom of the screen here. Handler, whoa, that's not at all. Handler dot first image left dot shape. They're the same. Okay, so we're just gonna say depth dot shape. And then we're going to say dtype equals np.uint8 because that's what CV2 wants when we're making a mask. We're going to say ymax is the handler dot, we can do the same thing again, depth dot shape 0 and xmax equals depth dot shape 1. And let me just for a moment here, just print out depth.shape so we can see what we're actually indexing here. So obviously ymax is the vertical height. So if we just extract this number, then we know that that's the maximum height. And then similarly with the width, all we do is just take shape, index it to 1, then we have xmax. And then we call this CV2 function cv2.rectangle mask is 96 by 0, and then xmax, ymax. So what this is we're establishing the top left corner of the rectangle, and this will be the bottom right corner of the rectangle. And then pass in 255, which will, assuming the value that it's going to fill in there, and then thickness equals -1. And this is just how you do it. And so now if we say plt.mshow mask, okay, we can see that the mask is on wherever there is information in our image, and it's off over here where there's no information, which is what we wanted. So this is, let's see what the type of this mask is at this point. It's still a numpy.nd array. So I think that we could have just filled the numpy array with 255, because let's say mask.unique. I thought you could do that with numpy. Let me see here. Okay. Let's just say a histogram will do it. Histogram of mask. I probably should have said flatten. Yep, sure should have. So let's just interrupt that before it has a conniption and say flatten, because we just want to know about the numbers we have in this here mask. Still taking a while, and I must have too many browser windows open or something. I don't know what's going on here. Let me look at my task manager maybe. Didn't even do anything. Pops right up, of course. Anyway, so yeah, we can see it's just I think that these are the, it should just be 255 and 0. I'm really kind of like floundering on trying to make this point, but let's just index in and take a look at like the first row of this mask. So for val in mask first row, print val, and then we can probably not do this 1,000 times. if I is greater than, I don't know, say 100, then we'll break this. Okay, so it's all zeros, and then we get into the 255s over here. So as expected, we have 0 and 255 values. And so, you know, this using this cv2.rectangle function, it's probably a good thing to know how to do. And you can see that we didn't actually reassign to a variable. We actually passed the object, the NumPy array, into the rectangle function, and then the function modifies that and automatically reassigns it with the new values. So this is actually something that happens a lot with CV2 functions that takes a little getting used to. I think there is, like, you could pass it out here, maybe. This is for my own benefit. No. Okay, so that doesn't work. It works the way I said. We have our mask. We're moving on. You know, I think part of the fun, or part of why this video series is going to be useful for people, is the fact that I'm sort of explaining some of these things at length, because you really get to see what is all happening here without me just, like, you know, hand wavily assuming that you know things or whatever. And so, you know, just working through the whole process together, this is exactly what I had in mind when I started making this series. So if it takes a long time, you know, I'm hoping you're finding it useful. So anyways, now we have a function which gives us our disparity map that we made up here. And we also have another function which computes our depth from that disparity map. So we're not going to really need to do those things independently of one another, since the depth is what we're after in the first place. We don't care about the disparity unless we're getting depth out of it. So we're going to make a wrapper function to just go ahead and say, just go straight through from images to depth. So we're going to go stereo to depth. We're going to take an image left, an image right, one projection matrix, two projection matrix, matcher equals whatever you want it to be. We'll set it to BM because it's faster. RGB equals false. Verbose equals true, because we're going to need to pass those into the function. And we'll say rectified equals true, because that will be true in this context. I'm going to add a little space so that we can see things easier. And okay, so this should be a fairly easy function to write. We're just going to say disparity equals compute left disparity map. And we're going to take the image left. We're going to take the image right. And we're also going to take the matcher equals to the matcher. Really just passing arguments down the line here. RGB equals RGB, and verbose equals verbose. Clear. Maybe comment some of this code. I haven't been commenting anything. I hope y'all don't mind, since I've been commenting verbally. If you do want the more explicit documentation for all of this, it's in the Jupyter Notebook version of this tutorial on the GitHub. It's linked in the comments. And I really do recommend that you read through that entire thing, because there's a lot there that I broke down very carefully, and that I'm trying to do the best I can to review everything. And I think that verbal communication is definitely, there's just a whole other element to the conveying the information in real time, which I'm doing in these videos, and then having the Jupyter Notebook there, where I've explicitly typed everything out in its sort of crystallized form, so that they're both useful. But you should go read the Jupyter Notebook tutorial, and it will also be useful to you. You know, you won't get everything out of what I'm saying. So, and then we will decompose the projection matrices, show matrices. Yeah, and we're just gonna get a little copy pasta here, and I'll have to change all these to right. This is actually why I don't like copying pasting sometimes. It's like, okay, so that is correct. We have our stuff that we need, and then we're going to say calculate depth map for left camera. And also, since the notebook that has all the tutorial in it has all these functions, I'm not actually releasing the notebook that has just the functions because they're not any different. I'm sort of copying them over and just explaining what I'm doing over time. So don't be surprised if things look a little different when you get into the repository. Okay, so that should do it. We have just glued together all the work we've done so far so that we don't have to, you know, do things individually. Now we can just go ahead and say, okay, I've got 2 images, I need the depth, kaboom. And so I can see over here that we are starting to get up there in time. And so I was, you know, didn't know how long any of this was going to take, but at this point, I think it's going to be a good time to call it. But let's go ahead and test this function real quick just to see it in action. And we'll just say depth is equal to stereo to depth, and we'll pass in handler dot first image, image left, handler dot first image right, and we'll pass handler dot p0, handler dot p1, and matcher equals, let's do sgbm because I like it better, and rgb equals false. I really have to put these in there because yeah, we don't want this to be true by default, so I'm going to set that to false up there. But in this case, sure, we can make it true, and rectified is going to be true, so let's just not bother passing that, and we'll do plt.mshow depth and turn the grid off because I hate it. And there we have it. So that is a nice stopping point for this video. We have gotten to the point where we can estimate depth from our stereo images. And as you learn from all of what I told you, explained earlier with the math that we're going to be doing, this is exactly what we needed. So now that we have a way to estimate depth in a frame, we can reconstruct, reproject points from our image frame, image plane, back into 3D space, establish their 3D locations, and then we'll be able to use a subsequent image frame to decide what the best solution for a rotation and translation of the camera that would project the points in 3D space that we defined onto the new image plane, and that'll allow us to do visual odometry and track the motion of the left camera through time. So that'll be the next video, where we will use this depth information that we get from the stereo cameras to reconstruct 3D space and then solve for our pose estimates that we will string along through time to give us our trajectory. So I hope you're finding all this very useful. I'm enjoying going through it, and yeah, we'll see you next time in the next video.